Hello and welcome to Module 5. In this module, we'll be talking about forms of energy, the first and second laws of thermodynamics, and energy in environmental systems. So when we're talking about energy, we want to recognize that most of the energy on Earth ultimately comes from the sun. You probably already knew that. There's a distinct difference between energy and power. Energy is the ability to do work, but power is the rate at which that work is done. So let's talk about the different types of energy. Kinetic energy is the energy of motion, and that energy is often generated when potential energy is released. So here are your definitions. Chemical energy, food is a good example. So we can see this energy on the electromagnetic spectrum. So recognize that here on the spectrum, these have a higher wavelength, a longer wavelength, right? And these have a much smaller wavelength. So you can see that here I've measured the wavelength of a very high energy wave. These would be maybe a gamma ray or an X-ray, and that's a very high energy. Picture me drawing this wave on the board. It would look like I'm taking a lot of energy to do that, right? So high energy, short wavelength. And these are the ones that can penetrate the skin over to the left here. They have short wavelengths. On the other side, the infrared, radar, cell phones, Wi-Fi, radio, these are very long wavelength. They look kind of relaxed, low energy, long wavelength. The ones that are used for photosynthesis to bring energy into the system are just this small little piece of the pie here, the visible light spectrum, and that's what's used for photosynthesis. So this again should be review. Okay, so when we're converting energy, this is something that comes up on the FRQs for the AP exam quite a bit. So please read this over, understand it really carefully, and then I'd like for you to do the your turn as your homework. I will check that when I see you in class next time. All right, when we're talking about energy and energy conversions, we often go straight to the laws of thermodynamics. So we're going to talk about the two laws of thermodynamics, or two of the laws of thermodynamics, the first and the second law. So the first law states that energy cannot be created or destroyed, but it can change form from one to another. And I've made a couple of notes about that. So when food is grown, the solar energy is converted to chemical energy, and that is stored in the plants. So if you think about that, the amount of solar energy that is available in an environment, that is what's going to determine the amount of chemical energy available to the food. So if solar energy is limited, that would mean that food is limited. That's why you often see most of the farms are closer to the equator. They're not up by the poles where there's less sunlight. When an animal eats, it converts the chemical energy in its food to kinetic energy that is generated by the movement of its muscles. When an organism moves, some of the kinetic energy is converted to thermal energy, which the animal releases as heat. The second law of thermodynamics is the same, says that while we do have the same amount of energy, that's the first law, but the system cannot convert all of the energy to working energy. So there is a loss of efficiency, and this would be the second law. So there's a loss of efficiency. So when we start to talk about different systems, we'll talk about the first and second law and how these systems can work more efficiently. Some of the forms of energy that we'll be talking about: gasoline, wood, coal, natural gas, solar energy, nuclear energy, chemical energy, and food, water, and wind. And again, this is a picture of what's happening in the second law of thermodynamics, where there's some energy given off or lost as heat, so it is not used as efficiently. Only 5% will come off as light in this picture, in this diagram. Okay, when we're talking about systems, it's really important that we talk about the whole system rather than just the parts of the system. And that way we can understand how a system works and functions. We need to know how all of the parts interact with each other, not just the sum of its parts, but it's defined by the nature of the interactions among its various components. And this is going to come up a lot in environmental science. It's important that we always look at the whole system. All right, when we're looking at systems, we talk about open versus closed systems. And what's the difference? In an open system, exchanges of matter or energy occur across a boundary. So like a lake will interact with the surrounding land and atmosphere. But a closed system, say an underground cave, matter and energy exchanges do not occur across boundaries. So obviously most systems in our atmosphere are going to be open systems and interact with their surroundings. Let's talk about a cow system. Here's a picture of a cow, and these are the inputs that are going into this system. The inputs would be water, grass, sunlight, oxygen. Outputs would be water, waste, heat, and carbon dioxide. So this is a cow system, the inputs and the outputs of the system. Sometimes we talk about whether systems are in a steady state. And a steady state means that the inputs equal the outputs, and they're not changing over time. So the system is staying the same and not going through a change. So we could look at our cow system and talk about whether it is in a steady state. If it was in a steady state, we could, if we want to know if it was in a steady state, we could measure and compare the water that the cow drinks against the total water released in urine, sweat, milk. Or we could look at the nutrients that it's eaten in the grass against the nutrients lost in the waste, and we would know whether this is in a steady state. All right, feedback loops. When we're looking at feedback loops, they occur as a result of a process returning back to the system, and they change the rate of the process. So they are part of a process. If something is going back to the same process, it changes the rate. A negative feedback loop provides a mechanism by which organisms or ecological systems can return to a steady state. Positive feedback loops will amplify the system. So it's important that we recognize this is not good versus bad, positive and negative. This is not the case. So let's look at a couple of examples. Here's a very basic one. If you have money in your bank account and you add money, your balance will grow, right? As your balance grows, you're going to earn more interest, which is going to make your bank account grow, which is going to make you earn more interest, which is going to make your bank account grow. So you can see that if this was on a graph, it would go up and up and up and up very quickly. Here's an example of a negative feedback loop. If your body temperature rises, you will start to sweat, and that sweat will bring you back to an equilibrium, make your body temperature drop. So if we again looked at this on a graph, your body temperature would go up and then it would return to a steady state. So this keeps the system at a steady state. What does this have to do with the environment? Here's an example of a positive feedback loop. If the environment starts to cool, ice will grow, more ice will grow. And that will increase the albedo. We have not quite talked about albedo just yet, but it is the reflection of sunlight off of the Earth's surface. This will allow less solar energy to be absorbed, or insolation is solar energy. Less solar energy will be absorbed, which will increase cooling, which will increase ice growth, which will increase albedo. You see what I'm saying? It goes around and around. Same can be said for warming. As the environment warms, ice will start to melt. This will decrease the reflection of the sun off of the Earth's surface, and more solar energy will be absorbed, which will add more warming, etc. So this is a cycle that will continue to go around and around. A negative feedback loop would be if the Earth is warming and that increases weathering, which will make a weaker greenhouse, which will bring us back to a steady state and increase cooling. So notice that this is not a circle. Same here, cooling, decrease weathering, stronger greenhouse will bring us back to a steady state by warming. So a negative feedback loop is not a circle, and this is unlike this figure here, 5, 10, because this makes it look like both are a circle. And this one you can see the population increases, which adds more births, which makes population increase, which makes more births, goes around and around. However, here it doesn't really show you that the circle is broken. So the lake level rises, and then the lake level drops. There shouldn't be these arrows here. I think this is a little confusing. So I wanted to specify that. All right, that's it. That is Module 5. Hope you enjoyed it.